Hey, feeling powerful? Look at what I've got for you here. Indices, powers or exponents. Here's a chance to work with powers of numbers. And there are three names for these. The index laws or the indices laws, plural of index, power or exponents. And I wonder if you've seen it before. When you get a whole lot of 2's multiplied together, there are 5 here, you can abbreviate that to 2 raised to the power of 5. This is called the power, the index or the exponent. And the number that you're raising to that power is the base. This is not a bad shorthand notation for situations where you've got lots of the same number multiplied together. And there's some interesting problems that come about from this use of this notation. And have a look at this little puzzle here. 1 is 1 cubed, then the next two odds added, 3 plus 5 is 8, is 2 cubed, or 2 by 2 by 2, check that out there, and 7 plus 9 plus 11 is 27, which is 3 cubed. What would the next rows be, and would they keep being able to be written as powers of the next numbers, the cubes of the next numbers? I wonder. That's an interesting result. I've taken that one from Pearson's, and in Pearson's there, we're going to talk about the work they're doing in Chapter 12, Part 6, 12.6, if you'd like to have a look at the reference there in the textbook. So we've created something here in Powerland, and what I want to do now is have a look at the consequences of that. Because we are writing, let's say, 2 by 2 by 2, which would be the same as 8, and then multiplying by 2 by 2, which is the same as 4, the answer is 32. And what is that? That's how many 2's here all in a line? It's 5, so it's 2 to the 5th. Often people define the power as the number of times the base is multiplied by itself. It isn't actually that, is it? Because 2 to the 5th is not 2 times itself 5 times. It's really only 4 more times, isn't it? Getting a little bit technical there. But this is actually the number of 2's in a row that we're summarising there. And gee, isn't that better than writing it out in full? Okay, so if we go into this Powerland though, what sort of stuff happens? Well, you might say, well, 2 cubed by 2 squared. I don't want to keep writing it out like this, going back to the full notation. I'm in Powerland. I should be able to shorten it and stay in Powerland. So what do you reckon the answer is? Well, we've done it up here. It's 2 to the 5th. I want you to think about this problem now. 2 to the 4th by 2 cubed. And can you write that out in full? I want you to pause the presentation now and see what you reckon that comes to by writing it out in full. Okay, let's do it now. 2 to the 4th means this many 2's. And then we times by 2 cubed, which is this many 2's. So if we count up the 2's, 1, 2, 3, 4, 5, 6, 7, it's 2 to the 7th. Hey, we don't want to go and do all this every time. We want to stay in Powerland. Can you see how you could have gone from there straight across to the 7? What's your conjecture? Do you want to do another one just to make sure? What's, 2 squared by 2 to the 5th? It's 2 by 2, that's 2 squared, times 2 to the 5th is all of this. This is very boring. I like the Powerland stuff better. And so how many 2's you got? 5 there and 2 there. It's 2 to the 7th. Hey, can you again go straight from there to that power? What are you going to do? Make a conjecture. Now, conjecture is a general rule that you would follow. So if I had any base raised to a power, and then the same base raised to another power, and I'm trying to multiply those together, what's your conjecture? A to the what? Pause the presentation and think about that. All right, so what is it? It looks like we add up the powers. There's our first rule, so that when we use this shorthand notation, we can stay in Powerland. We don't have to go back and write all these out again. So that's pretty handy. We're developing something interesting here. So that's our first rule for powers. Let's keep going and see what other things come out of this. What about when we divide two numbers? Okay, let's divide 2 to the, what's that, 2 to the 5th by 2 squared. Is that what we've got there? I think so. Let's go into Powerland because this is very untidy. So this would be 2 to the 5th over 2 squared. Now, let's see what it comes to when we do it by dividing. We'll cancel 2's and 2 goes once, those 2's. So it comes to be just 3 2's times. So the answer in Powerland should be 2 cubed. Hey, could we have stayed in Powerland? We don't want to write all that out. Could we have gone from there straight to there? What do you reckon? What about another one? What about 2 to the 4th done the old way over 2 cubed? This is 2 to the 4th over 2 cubed. What's the answer? Okay, try and work it out now. Let's pause it and let's see it here. They're going to cancel. It's just 1 2 or 2 to the 1 if you like. Hey, could we have avoided this and stayed in Powerland? What would we have done? Okay, I want you now to make a conjecture. So pause the presentation, and this time we're going to have to make our conjecture. A conjecture is a general statement summarising what we feel would happen because we've observed inductively, that is, from taking examples, something going on. And what's our proposition here? What's our proposition? Pause and write down what you think your conjecture should be for an expression which is a power of some base divided by another power of the same base. Clearly the bases must be the same. What? Well, have you done it? It's a to the m take n. So there's our second rule in Powerland. Remember what we're doing. We're trying to stay away from going back to writing out many, many letters all together. We're going to call that a to the m, if there are m or a's here. M lots of a along there. We're going to do that. Now, once we're in that mode, in what I'm calling Powerland, let's stay there. And if we can develop enough rules, we never have to go back and unravel what we mean by a to the m. Can you see the idea? Let's do another one. What about if you've got a whole lot of a's, so let's write them out now. Let's say we've got 4, a to the 4th, and we want to, let's say we square it. Let's have a look here. A bit of trouble just there. And we want to square it. What does that mean? Well, that's a to the 4th squared. Don't know what to do with that in Powerland. But over on this side, we could say that this is a... Oops, hang on, let's just try and come down here a bit. A by a by a by a. There's 4 of them in a row. Then if we square it, squaring it means multiplying it by itself. Like that. Oh boy. What would we have? Let's count up the a's. 1, 2, 3, 4, 5, 6, 7, 8. A to the 8th. Now, we don't really want to do this. We want to stay in Powerland. Could we have done something there to get our answer? Can you see it? Let's maybe do another one. Let's do a by a all cubed. What does that mean? Which means a by a multiplied by itself 3 times. Cubing means you get the number repeated 3 times. And what would this be in Powerland? This would be a squared all cubed. What meaning could that have? Well, let's have a look down here, doing it in the old way. 1, 2, 3, 4, 5, 6 a's. A to the 6. Oh, could we have stayed in Powerland? Could we have gone from there to there without going back to what we've been trying to summarise in Powerland, and that's repeated multiplication of numbers? Could we have done it? What would be your conjecture for a to the m all raised to an n? So making a general rule, not looking at any particular values of a and m and n, what would be your conjecture there? Okay, pause the presentation and see what you think. Well, what have we done? We have multiplied the powers together in each of these cases here. And later on, I'm going to set up a little proof so that you can see why that might happen. All right, what else might we want to do? Well, let's have a look at one situation here, which is a rather special one. What if we've got 2 by 2 by 2 by 2, which is 2 to the 4th, divided by 2 by 2 by 2 by 2, which is another 2 to the 4th. Let's work out what this side comes to. They all cancel. It's a number divided by itself. So it must come to the number 1. But hang on, we've got a rule. For division in Powerland, it's the numerator power minus the denominator. We did that before. And therefore 1 equals 2 to the 0. Hey, this is getting funny. Can you see what's just happened now? We've gone into Powerland and we want to develop a whole theory on how to work with numbers as powers, and we've found a rather oddity coming up here. If we accept our earlier rule, a to the m on a to the n is a to the m take n, we want that to be upheld throughout. We've got to be prepared to stay by it when it comes to this. So it would work as long as we're prepared to take on board that you may create, through this problem, a 0 power. Oh, okay, well let's define it then, as we now define it as a to the 0 being 1. Okay, because it's come up as a result of our developing theory here. We need to say, are we going to stick with this rule? If we do, we come across this and we get 0. So now we have to enlarge our definition of powers, because you can't define 2 to the 0 in the way we have defined usual powers earlier. It doesn't mean 2 multiplied by itself no times, as such. It has a special definition which is going to be consistent with what we've been doing. Just notice that it would work for all numbers, wouldn't it? Not just 2's. What couldn't you do here? What wouldn't be realistic? Can you see that we're dividing through by the base? Divide by the base. If it was 3's all in a row, they would cancel. So the base cannot be, because we're dividing, cannot be 0. Okay, because otherwise this definition here of y comes to 1 would not work, because you can't divide by zeros. So we have to put a little proviso here, provided that, or the proviso, PV for proviso, a is not equal to 0, because it's all based on division, this one. Now this is getting interesting. You thought powers were simple. Now we've got a 0 power. It's still simple, but it's interesting to see what's happening to our power definitions now. Let's do another one, coming from the same rule now. Let's say I've got 2 cubed and I'm dividing, hang on here, I'm dividing by, we might just have to move down a bit. We're dividing by, let's say, 2 to the 4th. 2 to the 4th. Here we are. Still a little problem in here, so let's try to write that a little bit better. This is by 2 to the 4th there. Okay, let's see what happens. This is 2 cubed over 2 to the 4th. Okay, if we cancel, they cancel, they go into there once. The answer on this side is 1 over 2. 1 over 2 there. If we can get that. So 1 over 2 equals 2 cubed over 2 to the 4th. Hang on. Yeah, I don't know how this works, because this, according to our rule, should be 2 to the 3 take 4. 2 to the 3 take 4, which is 2 to the neg 1. Hey, we're getting into interesting land here. So if we keep pursuing this rule, a to the m on a to the n is a to the m take n, a second oddity comes up. If there's more of the base in the bottom line, more of those, then you're going to get a negative power. Make a decision. Are you going to stick by this rule and keep sticking by it? If you do, you're going to come up with a negative power. And what would it mean? It would mean there were more 2's left in the bottom line in this problem. And so 2 to the neg 1 means 1 over 2, or 1 over 2 to the 1. Okay, let's do another one. Let's perhaps do one over here and do 3 cubed over 3 to the 5th maybe. No, do that one. This is 3 cubed over 3 to the 5th. Okay, let's cancel it again now. This is 1 over 3 squared in the bottom line. And what do we get if we use this power rule? 3 take 5 is our rule. Numerator power minus the denominator. So it's 3 to the neg 2. We're always going to generate a negative power here because the number of 3's in the bottom line is bigger than in the top line. Are you going to stick with it? 3 to the neg 2 means 1 over 3 to the 2. What's your conjecture now? What is your conjecture for a negative power? If we have a to the neg n, what's that mean? Why did you get a negative number of a's there? Remember, it was in the bottom line because the top power, come over here, was smaller than the bottom. So 3 take 5 gave a negative. So a to the neg n, would you like to make a conjecture? Pause the presentation and see what you think. In general land, in conjecture land, just using a and n, not particular examples, what do you reckon? Okay, it means 1 on a to the n, doesn't it? The negative number indicates there were more n's in the bottom line, and therefore a negative power means 1 over. All right, interesting results, and we might want to try and look at a better proof, a more general proof than that later on. Let's go down now and see if, from Pearson's how they summarise these rules. So we'll come down and we'll find all our conjectures are down here just in a minute. They're way down here. Here we are. And the ones that we've just looked at is this one, these are the crucial ones, and this one, and then this was a special case there that we looked at, and this one here. There are 2 others there that you might have a look at, and it's really to do with brackets, these 2 here. If you have a product, 2 numbers multiplied together and raised to a power, you raise each of them to the power. You do the brackets, you do the raising to the power to whatever's in the bracket. And in this one here, A divided by B and then raised to a power is the same as raising the top line to the power and then dividing by the bottom line raised to the power. And just quickly, you could write a little proof here, and I'll just do the first one. You could have what? MA's there, that would mean n terms, that would be the first one, times n terms, however many that is, n terms, so that would be a to the m by a to the n, and so that would equal how many terms? Total terms. So let's have a look here. I'll just put it down roughly here. So this would be m plus n terms altogether, m plus n a's, which by definition is a to the m plus n. So that's a little informal proof that you might like to look at, not assuming any numbers, so therefore it's a proof. And you could try to write some sort of proof down for all of these if you're a keen mathematics student. A proof means a general description, not assuming any numbers in there, and it's called deductive reasoning. If you use actual numbers to check things out, it's called inductive reasoning. And of course you must use deductive reasoning if you're going to prove something, so that people won't come along and say, oh, but that won't work if you put A is 3. Okay, so that's the idea of deductive reasoning. You say, hey, it doesn't matter what I call A and M and N here, this will always work. Let's go and look at a couple of examples. So coming down here now, again from Pearson, so have that book so you can refer to it. So we want to do this complicated expression. Remember what we've started. Instead of writing out numbers that are in repeated multiplication with themselves, we've used this contracted method of powers, and now we need to be able to do everything we want in Powerland. So let's have a look. There's a few powers here now. So looking at doing the brackets first, we're going to say a to the fourth all cubed. This is a to the m all to the m. What do? You multiply the powers. So you're going to get 12 there. Then it's just b to the 7. And then let's have a look here. A cubed all squared. It's another multiply the powers together. There's that rule. It's a to the 6. And then b to the neg 4 all to the 3, all to the 2, sorry, is b to the neg 8, multiplying them together. Now this is very crowded in here. Let's come out here and see what we've got. We've got this times this here. Now you can't use the rules unless the bases are the same. You can see that from our derivations there. So a to the 12 by a to the 6 is a to the 18, because a to the m times a to the n, you add the exponents or powers, and then times, what are we doing in B land? B to the 7th times b to the neg 8. We add them up. So it's b to the neg 1. Let's just check that here. 7 plus neg 8, adding the powers, that's what it says here. You add the powers, so 7 plus neg 8 is neg 1. Remember that now. 7, 7 on the number line, take 8 is going to land you down at neg 1. Just check your work with that then. And then we want to go a bit further. What is meant by negative power? It means 1 over that power. 1 over b to the 1. We don't usually write the 1 there. So you can see we're getting into some interesting problems here because we've chosen to use this power index notation or exponent notation. So we're developing an area of mathematics now to actually handle that form. Let's go down, have a look at another problem. So here, this is worked example 12. So getting quite big here. So the idea, of course, is that generally now you need to change these divisions and things a little bit. So we're dividing by a fraction here. Do you remember? 3/4 divided by 2/3. You invert the bottom line and multiply. So it becomes 9 over 8. Well, that's what we do in ordinary fraction land. division by a fraction, you invert and multiply. I wonder if you can prove that. Why do you do that? Well, I'll show you how it works. If we say here, multiply top and bottom here by, what can we do? We could multiply top and bottom by 3 over 2. Let's do that. Top and bottom by 3 over 2. Now, what have we done? Oh, when you multiply the bottom by that, it comes to 1. The top line is 3/4 by 3 over 2 divided by 1. So the answer is 3/4 times 3 over 2. So the idea there is that instead of worrying about actually doing the division, if we multiply top and bottom by the reciprocal here, that turns the bottom into 1. And therefore the answer is equivalent to the top line multiplied by the bottom line turned upside down. So we need to do that, and that's what Pearson's has done here. Dividing by n to the -5 on m to the 12, you have to invert the fraction and multiply. So we're now at that stage, and now we want to work out this bracket here. So we've got to raise each of these to the power outside. So that's m to the 8, n to the 4, m to the 20, n to the 12. And then we've still got our other powers over here. What can we do? Let's look at that top line. This is m to the 8, n to the 4th by m to the 12 over m to the 20, n to the 12, quite big this one, and n to the -5. So now we can collect up the m's. What do we got? m to the 20. Multiplication is addition of powers times n to the 4th, and in the bottom line we've got m to the 20 here, and n, add those up, n to the 12 take 5 is 7. So what have we got? These will cancel out, or just give m to the 0 if you wish, which is 1. And n to the 4th on n to the 7, subtraction of powers, remember, a to the m on a to the n is a to the m take n. So 4 take 7 is n to the -3. But what does that mean? It means there were 3 7s left in the bottom line, doesn't it? 1 over n to the 3. So there's a lot of work to be done here with fractions and expanding brackets and that sort of thing. All right, so we try to use a positive power at the end. So if you have n to the -3, it's preferable to say a negative power means 1 over and reduce it down to this form here. All right, let's go on and have a look at giving you a go. So here's the first question. So in this question, it's numbers together. Now you don't add the numbers. 4 times 3 is still 12. You've got to, though, add the powers. Multiplication is addition of powers here in Powerland. So we've got a few of each type here. Just keep the bases together, A's together and the B powers together, and go through that. Remember, you do the numbers together, and then the two, if there's 2 bases, keep the bases with equivalent bases, the same bases there. Remembering, do the expansion of brackets in this sort of thing. Do the 4th power to each of them. Or here, before you go on in M land, you must multiply those 2 powers together. Do the brackets first. Okay, we'll pause the presentation now and have a go. You want to do most of these, I think, and check your answers. If you're running out of time, perhaps just do the middle column. But the most important thing is to get the practice so you'll remember it. Okay, so pause it and have a go. Right, coming back now, let's have a look at a slightly harder problem, question 2. This has got divisions in it. So remember, division by a fraction is the same as multiplication by the reciprocal, or the inverse. So we turn this one upside down and multiply by it. So that's an old rule, a few years ago now. So you invert and multiply. Division by a fraction Here we are, dividing by a fraction. You invert the fraction and multiply. So that's what you've got to do. This is your fraction over here. I've just written over that K, so I'll just scrub that out there. So if you're dividing by this fraction, and this one in here, dividing by that, then you have to multiply by its reciprocal. Again, there's lots of problems here. You need to have the practice and see what you think. Okay, so pause the presentation now and have a go. Moving on, question 3, same rules. Got a few K's in there instead of numbers. Okay, so check that out, pause it and have a go. Question 4, getting a little bit harder, a bit of a mixed bag here. Same thing, lots of brackets. Do the brackets first and see if you can come up with these answers as you go. Pause it and have a go. Let's have a look at some of the harder ones here. 5 and 6. I don't think they are actually harder. A few negative powers. Remember your work with negative numbers. Okay, pause it and check that out. 7 and 8. Slightly harder ones here probably. Lots of practice. More practice you get, the better. Pause that and have a go. I'll come down to the end here. See some open-ended questions and see if you can work out what to do with these. Open-ended means you'll involve your own thinking here, and so your answers may not be exactly the same as these. You might have to check with a teacher to get some help with some of those. Alright, so can you see what we've done? We've created an interesting system of condensing it into a nice notation, and as a consequence have come up with some rules, and it's developing into all sorts of interesting things there with 0 powers and negative powers. Never thought they'd be possible. And later on we're even going to go further. This is only part 1, and so there's more excitement coming up in part 2, where we develop the exponent or power theory even further. But at the moment, until I catch you then, it's cheers from me, work hard and have some fun.